1100 minutes times 60 seconds per minute, and of course I had used 0.61 as our C naught. That's a good observation that you don't really need that. However, since we're asked to
I just thought of
calculate
that.
the diameter in A, B, C, D, E, B in one of our questions, we need that also.
Yeah.
So then we have 9.81 meters per second square. Square root, we have 10 meters in diameter. We have d squared times square root of 5 meters. Okay, that gives us a d of 0.05. 00 something meters.
Did you multiply the 2 by the g?
Say that again, what did I do?
I'm just confused as to why the 2 is,
2.
isn't it like,
What did I write? Did I write it wrong? Hold on. Yeah.
In the time
It's I switched it. It's the square root of g here and the g here. So I took this out and right.
Hmm?
So the equation I'm solving for, let me write it here. RTE is equal to 1 0 g. No wait. 1 0 times 2 over g times d tank squared, d whole squared. And then we have HL1 minus HL2, right? But this one was 0. Okay, so you're with me now? Okay, I just went from there. So that's our delta. I should write delta T, sorry. Delta T. Is that more clear?
yeah.
So for delta T and like delta H, why is it 1 minus 2 instead of 2 minus 1?
So it's you have to look at it. So this is not our typical thermo, right? We have in one we have a high level, right? So really what we're doing is we're looking at calculating the time to empty the tank at the highest level, and then we're subtracting the time to empty the tank at the second level. So it's not like our point 2 to point.
Okay.
It's just right. So it's obviously it's going to take a lot longer to empty the tank from the higher level than it is from the second one. So, you know, I'm not sure that this is the best way to write it because you're so used to 2 minus 1. As long as you keep track of which one. I mean, obviously, if you get a delta T of negative something, you know that okay, I've switched it. So what did I say? So I just skipped a step, right? Our delta T is equal to that, and I should not write this as TE. It's delta T. Okay, so that it's not confusing. Right? It's just that this one is 0. So, and our D in this case is equal to 0.0501. Or, okay, that is in meters, which is 5.0 centimeters. That's the area of the hole, and then we can put this back into our QM max. So that's our part, no, actually, that's part, that was part D. This was actually E. We were asked to calculate that after. Because you can actually use the diagram, right, to get the slope and estimate it from there. But I don't know, I feel this is more straightforward in my opinion. Okay, so our QM max is our row A, so this is area of the hole. Not to be confused with the tank, right? GHL0. And specific gravity 0.9 times 1,000 kilograms per cubic meter times 0.0501 squared on 4. Okay, so we're using the C naught the same as we had used in the other one to calculate D, right? And max then is 10.711 or 11 kilograms per second. Okay, so C naught equals 6.1 probably. Most realistic. C naught equals 1 would be worst case scenario. But it's for a rounded hole, right? But for smooth hole, and normally you will not have a smooth hole, right? Any questions? About this problem? Okay, and I think that I'm gonna let you, hopefully this is everyone, can I turn on this again? Everyone catch up with the writing? Yeah, I'm writing slow, so. Okay, so this is a somewhat older exam problem, so this is not one that you have already.
Can I see his book? Why? He's taking a picture.
But I want you to, I want you to think about this before I actually tell you how to solve it. Okay, so we have a large 5 meter in diameter, 10 meters high tank that's slightly pressurized at 0.1 bar gauge storage tank, and it contains acetone, giving the molecular weight and the density. So the molecular weight you can find in the book. That may not be given on your exam. Okay, so just make a note of that. It's in one of your tables. I can't remember if it's in the one that actually have flammability data or if it's in the one that has the threshold limit values. But you can get that from there. And if it's a pipe problem, you would also get the viscosity. Okay, you might get the viscosity even if it's not a pipe problem, but it's located near other equipment in the plant, and the hazard analysis reveals that there is a risk that nearby equipment can come too close and puncture the acetone storage vessel. So it's therefore necessary for you to design and build a dike to contain the acetone in case of a spill. And it's estimated that nearby equipment will be most likely to penetrate the storage vessel at a height of 6 meters off the ground and leave a hole 1 inch in diameter. So if it says a hole 1 inch in diameter, obviously you can assume that it's a square hole if you want, but it's most likely circular, right, or a round hole. Unless I actually says that it's punctured by a forklift that leaves a 1x2 or something, 1x5 centimeter hole, right? If you only have something like that on the quiz that said 2.5 millimeter hole, it's most likely round, especially if it's due to rust.
Do we have to like declare whether or not we're assuming like one way or the other, or would that be? Like, figured out?
You know, it's obviously it will be clear
Yeah.
from your calculations what you assume, right? But it's always better to clearly state your assumptions, because that way you're telling me that you know what you're doing. If you're just putting all the numbers in there, I mean, if it's something, if it's geometric, right, it doesn't really matter that much. But if it's assumptions for C naught, for example, I need to see that you know what you're doing, right? Why you're selecting certain values over others. Okay, so if the maximum diameter of the die is 9 meters due to nearby equipment, what is the height of the dipole that would be required to contain the acetone? Okay, so see if you can draw that first. Questions on that?
Would the acetone be all the way, like, would it be completely full? Or does it not matter to the
So the question is, will the acetone, will the tank be completely full?
Because I mean,
So
depending
it's
on
not-
how,
Yeah.
like, how much there is, it's only
Yes.
gonna reach up to 6 because that's where the hole is. So whatever that much is how
We
much
still
is
need
used.
the height of
No, I know, that's why I'm asking.
So here's there's a lot of things into this, right? So I haven't told you what the liquid height in the tank is, which means you're going to have to assume worst case scenario, which is that the tank is full at the time the leak opens up, right? Because that would give the highest flow rate out of the hole. Right, now, of course, and I made a note of that it is not likely that any storage tank is full to the brim. Because that is, if you have a change in temperature, you could overpressurize that tank, right? Unless it's vented, you know, so you have to be, there's some headspace that they always leave. But that would be our worst case scenario, that it's completely full. Right, yes?
Is the diameter of the outer wall, does that take into account the inner diameter of the tank already?
So when I say the maximum diameter of the die, that is not, right, so here you need to know what you're looking at. You have a tank that sits on the ground. I don't know that I specified that, but we're gonna assume that. That's most likely. If it's 5 meters in diameter and 10 meters high, it's probably on the ground, right? It's a pretty big tank, right? It's not raised. And if it was raised, it would state that in the problem, if it was off the ground. Okay, so the diameter is the diameter of the die. Okay, it's restricted due to nearby equipment.
But I mean, like, does it take into account the diameter of the inner tank? Like, is it,
So they concentric.
so, yeah, is it concentric in the way it's measured that way?
Very good. So the question is, so here's what you don't know, right? In terms of, you could envision, okay, right? I know the hole is gonna be on this side, so I can place a tank on this end. And then I have, right, the total dike area is 9 meters, but I have this much. You probably don't wanna do that, right? You probably do wanna put your tank in the middle, concentric. And then your secondary containment, which is the dike then, right, which is just basically, you know, we have some wall here to contain it. Right, so that's the geometry that I was looking for. It's not, right, it is
Okay.
really difficult to write an exam problem that's not, right, that's completely unambiguous, right? I have noticed over the years. I have something in mind and then, you know, it's not, right, that wasn't clear from the problem, but this is most likely because, you know, you can, at first, we don't know what side the hole, that there is a chance that it's most likely that it's gonna be penetrated from one side. But, you know, what if it could be equally likely that it's penetrated on the other side, right?
I have a weird question. How different would it be if it was like pierced right through and if we had two holes on the side? Versus really just
You would have to sum the holes, right? That would be equal to having one larger hole of the same size. I think that would be what we have to assume. Now, you know, that's not very likely, but on the other hand, there are, I was gonna say, there are a lot of things that have happened are things that are not very likely. Yes, they do happen, right? You have a question?
You know, wouldn't it behoove these people just to get rid of these like hazardous pokey materials?
Yes, yes, right. Restrict your forklift driver so they're not near a storage tank in the first place.
We put like a
Right.
boundary up or something?
But yeah, so there should be barricades so you can't run into it. But, you know, you'd be surprised at what actually takes place at sites.
It just
right?
seems like digging a big hole would be like the last thing I'd wanna do.
Yeah. So, but, you know, if we look at some of the accidents that have happened, you're baffled over how things really, you know, what was the actual trigger on some of the things. So clearly, right, if you have workers having to work around the tank, the best is clearly to make sure that you restrict their access or decommission the tanks at the time. Empty it if there's any, if they're, right, if they're moving. If they have these large things, they're moving, right, swinging around, you just wanna make sure you can't hit the tank at all. Okay, so that was the first part of the problem, right, to try to figure out what the geometry is here. So we have, it was 5 meters here, and the maximum that we could build here was 9 meters. Okay, so we're just assuming that they're concentric. It's 10 meters high. And then we had the 6 meters here. And then we're asked to design this to contain all the liquid. Okay, so it just said to contain all the liquid. So one of the first things, so if you remember our problem here, we have 2 things. First, it needs to contain, if it's full, it needs to contain all this liquid, right, that leaks out. That's the first thing. It can't overflow. But if you calculated that, you'll see that that will actually be smaller, right? That's why I put it at 6 meters, okay? Than this leak, right? Remember our problem for, was it 4.6, I think it was, where we actually calculated it. So I have actually not given you that information. If you notice the hint that we had in that problem. But, you know, hopefully from remembering that, you would remember the time for the time to reach the ground from a level, right, is equal to this. Okay, but the problem is clearly, right, it's clearly flow of liquid through a hole in the tank. Because if you do the, okay, so the dike, by geometry, this dike can hold all the liquid, okay? The dike can hold the volume of liquid. Hold total volume leak. Is that clear, what I mean with that?
With like a really small height.
So let's just look at it. So what we have the liquid that's leaked would be 10 minus 6 if it's full, times 5/2 squared. It is